Okay, oxidation. Today we are talking about oxidation, also what is oxidation, redox reaction, what is the ORP?
Exactly. Free chlorine versus redox, what is the difference? Then,
especially also about the DHN, disinfection with free radicals, the most powerful oxidations. But really a key one will be about corrosion. What is corrosion and where it's coming from?
And the famous Frenchman, Monsieur Langelier, huh?
Yeah.
Okay.
Langelier, how you call it? Langelier Index.
We have to ask Florent. Anyway, and that's always, we take your questions at the end of the session. You have this option to participate. Please use the chat function here to write down your questions as we go through the presentations. And as always, all of our sessions are recorded. You have an option to review them on our website for a period of 7 days before it's replaced with the next one. And you will find it's over here, program for the remaining sessions. And as always, copies of our PowerPoints on our website as well.
Proud of you. Yeah? You're getting better and better.
I get better and better at this.
Good.
So, Dominic, what is an atom? Let's start very small, huh?
Okay. Give me the command. Okay. For example, you have a glass of water, right? Water is it's a amount of molecules, and the molecules of water is H2O. This is the molecules. This is the molecule, and the water molecule consists of two atoms. One of them, for example, so there are two hydrogen, and one of them is oxygen. Mm-hmm. So let's have a look on this oxygen. Each atom has a nucleus, and in the nucleus you have the protons, which are positively charged, and you have the neutrons, which have no charge. This is why they are called neutrons, but they really give the weight of the atom. And then the atom is surrounded by electrons, which are in a outer layer, right?
Shell.
So in a shell, like an atmosphere. It's like an atmosphere. And for example, if you have a look on the oxygen atom, you have here, you have the nucleus with 8 protons and 8 neutrons, and then you have 8 electrons. You have on the first shell, you call it shell, Philip? You have 2 electrons, and on the outer shell, Florent, how you call this? Valence electrons?
Yeah.
Valence electrons. You have 6 valence electrons. These are the electrons on the outer shell. Let's have a look on the periodic system, and on the chemical periodic system, I would say. So here you have all the elements that we know, or at least I know. You start here with the hydrogen, which has 1 proton and 1 electron and 1 neutron, and then you have here the helium, and then you go on the next period.
Yeah.
You have then the next one, and here you have these different groups. For example, oxygen is here on the 6th. You make 1, 2, 3, 4, 5, 6 on the 6th group. This is the oxygen group. So that means the oxygen has 6 electrons in the outer shell. If you take something else, for example, chlorine, it has 7 electrodes in the outer shell. So it has 2 on the first, it has 8 on the next, and 7 on the third layer on the outer shell. Now these are, by the way, these are the halogens. You remember the trimethanes? It's coming from the halogens. So these are the halogens. Fluorine, chlorine, bromine, iodine, these are very strong oxidants. Where is that coming from? This is coming from the electronegativity. This is the number that you see here. You don't see it really well. So for instance, chlorine has here a number of 3. This is the electronegativity, or atomic oxygen has 3.5. This is the electronegativity. this is with what force it wants to get another electron. Because they try to get to the noble gas state. These are the noble gases here. You see they have no electronegativity because they have here 2, and all the others have 8 electrons in the outer shell. It's maybe a little bit complicated. Huh?
Yeah, it is a little bit. But I mean, what are you trying to say? I mean, the more on the right, basically.
Yes.
Huh?
The more on the right, you know, the more on the right, the higher is this electronegativity. The more they want to get an electron. And this has to do something with oxidation. And by the way, you know, again, if you compare here fluorine with oxygen, 4 to 3.5, it wants really to get higher an electron. And if you go one below, fluorine is fluorine. Okay, fluorine is has a higher electronegativity than chlorine, and chlorine higher than bromine. So the lower you go in the period, the less you have this electronegativity. That means the more you're here on the right side, and the higher you are, the stronger is this oxidant. The more it wants to grab an electron.
Okay, so let's explain maybe on the next slide what oxidation means. Huh?
Okay.
You ready?
Yeah.
Okay, so what does that actually mean, oxidation? Oxidation means the transfer of electrons, right? So you have 2 agents. They're called agents. You have an oxidizing agent, and this oxidizing agent actually wants to get an electron. It's, as Dominic explained, it's not complete. It wants to become complete. So it's looking for an electron, and it finds this in a reducing agent. The reducing agent is what gives the electron, and this really makes this complicated. Maybe this is why we drank so much whiskey yesterday, because an oxidizing agent is reduced, and the reducing agent is oxidized. This is crazy.
Yeah,
but,
that's a bit, but I mean, just concentrate on the left side. You know, the oxidizing agent, that's, for example, chlorine or bromine or fluorine.
Yeah.
I leave out the fluorine because I can't spell it the right way. Wants to grab an electron, right? And the reducing agent, that would be an organic, for example, urine or sweat or whatever, you know, which will donate then the electron. That's all about.
That's what this is. So the redox reaction is the reaction that takes place between an oxidizing agent and reducing agent. And this always has to be complete. Huh?
There is no oxidation without reduction.
Exactly.
It's always something grabs an electron and the other gives the electron. This always goes together. And this reaction we call redox reaction, from reduction and oxidation. That's the redox reaction.
Exactly.
Yeah. Good.
Yeah. And so let's now, you said the term redox. There's also a term called ORP, oxidation reaction potential. They are synonyms.
Oxidation reduction potential.
Reduction
this
potential.
Is ORP. ORP, oxidation reduction potential.
So
ORP.
what does that mean, right? So we have oxidizers on one side, and we have reducers on the other side. And the more oxidizers you have, the higher is that ORP, that potential. And this potential can actually be measured electrically, and it's expressed in millivolts.
Yes, and again, you know, you have here up, you have the oxidizers. So the more oxidizers you have, the higher is this ORP. And you have below, you have the reductants. So chloramines, organics, cyanuric acid, urine, these are the reductants. The more you have from this, the lower is this. Oh, it's like a relation. Above oxidizers, below the reductants. Yeah, so oxidizers, if you increase here, for instance, chlorine, hypochlorous acid, or ozone, the higher this ORP goes. And if you increase here, so if you pp, for example, in the water, then your ORP goes down.
Yeah.
Huh?
Yeah.
Yeah.
Yeah. And that's the ORP, and
Yeah.
it's measured in millivolts.
Yeah,
Huh?
and oxidizers, as we wrote here, hypochlorous acid, ozone, hydrogen peroxide, potassium monopolar and all the kinds of chlorine, you know, the sodium hypochlorite and the tablets, and yeah, some of them are a little bit stronger and some of them are a little bit weaker. But I think this is important to understand. ORP does not give an absolute value how much of chlorine, let's say with chlorine, you have in the water. This, it will not tell you, but it's a really good indicator, you know, how good your disinfection is working. So it gives, it's a good hygiene parameter. And it's really it shows you how efficient your disinfection is working. You want to explain here this graph?
So a hygiene factor telling us how effective it is at killing organisms, microorganisms in the water. So, for example, we have here on the left, we have the ORP potential expressed in millivolts. And on the horizontal, we have the kill time in seconds. And this is always kill time 99.9% of all microorganisms. So if we look at this, if we have an ORP of 600 millivolts,
650
millivolts, thank you, then our kill time will be just a little bit, 30 seconds, to kill 99.9% of E. coli bacteria on this example. If you increase your ORP to 700 millivolts, then the kill time is reduced to 5 seconds. This is the difference. So as a consequence of this, we have, for example, drinking water is usually has an ORP of 650 millivolts, whereas in pools we need a faster kill rate, so it's usually between 700 and 720 millivolts. Yeah.
Rules, right? And this is for E. coli. So for other microorganisms, this is different.
Yeah.
But this is why, you know, usually you say in drinking water, roughly 650, pools, roughly 700. Okay, let's go to the next slide.
Okay.
Now, we also have to see that the ORP varies also, for example, with pH or with temperature or with turbidity. Let's start with the pH. Here you see an example. You have the free chlorine. It's a little bit in these fancy colors here. So let's say we have a water, it's 0.4 free chlorine, right? You have a redox potential, you have a pH of 7.6, and now you get your ORP reading, let's say it's 650 millivolts. You do not change the free chlorine content. You leave it at 0.4, but you drop the pH to 7. We know that chlorine is more effective at a lower pH, and you see that the redox potential will increase by 700 to 700 or 720, just as an example. So that means you always should, if you control your pool with ORP, you also should have really a pH control.
Okay.
That's in a way important. And we also mentioned here water temperature and turbidity. Let's go maybe first to turbidity.
Turbidity.
You want to take that, or?
Yeah, okay. So this shows us the correlation between pH, redox, and zeta potential. Remember, zeta potential is the charge between particles. And, you know, you look at this here, if we have a neutral pH, that also means we have a neutral zeta potential, which means we have no or little charge between particles. We have big particles,
and this is why
clear water.
Yeah, this is why the particles are coming together. You know, instead of having 1,000 smalls, you have maybe 10 big.
Exactly.
And that's also less turbidity. The water will become clear. Remember session number 6.
Yep.
So the high, if you go in a high pH, you have a high negative seated potential. If you have a low pH, you have a high positive seated potential. Not really important. Important is if you have a neutral one, you get less turbidity. You have less particles, maybe bigger particles, but less particles. And this is also increasing the redox potential.
Yep. Yep.
Good.
Very good. Okay. So now you mentioned redox and it's not free chlorine, right?
Maybe the last point where we do not have a slide is about temperature. And
Yes.
At low, the lower the water temperature, the higher is the redox potential. This has something to do, that was in session, Florent, where was it? 1, I think. You know, you remember we said at 30 degrees, you know, the growth rate of bacteria, the doubling rate for heterotroph bacteria, if there is enough food, is 30 minutes. If you are on 20 degrees, it's 2 hours. So the higher the temperature, the quicker is the biological growth. And this also you find then in the redox potential. That means also, you know, if you control your private pool with ORP, and you start in springtime when the weather is cold and maybe the pH is not yet stable, and you said, okay, I go for a redox potential of 700, and maybe you measure manually the free chlorine. Maybe the free chlorine is only 0.2, 0.3. And then the water temperature goes up, maybe also pH goes a little bit up. And 4 weeks later, you check it again, you still have 700 millivolt of ORP. Maybe your free chlorine is then 0.6, 0.7 or 1.0, which is okay. Because then you need higher amount of oxidants to have this 700 millivolt of ORP, of redox potential. Okay, but that brings us now to this slide. You know, what is better, redox or free chlorine? Yeah,
it's hard to say.
Hard to say.
Yeah.
It's something different. ORP gives you the power of disinfection. The red point here, the power of disinfection, and the free chlorine measurement gives you the absolute value. So if you are in public pools, very often you're regulated. In Switzerland, Germany, we have public pools. We run them between 0.3 to 0.5 free chlorine. It's impossible to regulate this with ORP. It's absolutely impossible, but still, so this is why you use their free chlorine sensors. Free chlorine sensors are more expensive, roughly 1,000, 1,500 euros more in cost. Yeah, they are a little bit more difficult to calibrate. Ideally, you know, you have in a public pool, you need this free chlorine, you know, that you can stay in this band that is given by the legislation, and this is why you have their free chlorine. Ideally, also redox. So you regulate it with the free chlorine value, and you double check with the redox. Yeah.
So for a residential pool, private pool, redox is great.
I think it's great.
It's ideal.
I think it's great, but it's not something where you can say, well, I have 0.2 or 0.3 free chlorine. You can, if you want to do that, then you really need free chlorine. But yeah. So again, free chlorine does not measure the disinfection power. It measures the absolute value, and ORP does not measure the absolute value. It measures the disinfection power. The ORP will depend on the load, on these organics, below the relation. Strich,
the line.
The line, below the relation.
Yeah, exactly.
So it depends on the load, it depends on the water temperature, it depends on the pH, it depends on the turbidity, on the seated potential. But I think it's perfect for private pools. Not for public pools. There, by law, you need free chlorine. And in our Daisy Plus that we call swimming in drinking water, we also would recommend free chlorine.
Okay. We were talking about different types of oxidizers, right? And the different strength that they have. This is actually measured as electron volt. It's the electrochemical potential that these oxidizers have. And here's a really good list that compares the strength or the force that these oxidizers have to attract other electrons. So the strongest that are used in a swimming pool, can be used in a swimming pool environment, are hydroxyl radicals, free radicals, followed by atomic oxygen, and so on. You see ozone. Chlorine is actually relatively weak compared to some of these other ones.
It's not weak. The other are very, very strong.
Okay.
It's very, very strong. And with these free radicals, by the way, it's the hydroxyl radicals and the atomic oxygen that we call free radicals. Both of them are free radicals. You know, everything which is above 2, you know, you usually have a complete oxidation. And the lower you go, the more you have not complete oxidation. You have substitution reactions where you also can form a byproduct. But that also depends what is the reductant, what you want to oxidize. So some of these molecules are easy to oxidize and some of them are difficult to oxidize. But yeah, maybe go one back. Again, you know, if we look at this, you know, for instance, this is an organic compound, urine or whatever, you know, and here you have 2 electrons, you know, the 2 carbon both give an electron. So this is like 2 hands.
Double bond.
Double bond. And now this hydroxyl radical or the ozone or also the chlorine, you know, they take one away. They take one away. And this is how you split this in 2 molecules. This is the oxidation process. And as I mentioned, you can have here complete oxidation. For example, maybe with hypochlorous acid, you make a complete oxidation of this organic compound. That means you really grab the electron completely away and you split it. You don't rest with it's not a substitution reaction. And if you get a tougher one, for example, here this methane, you know, with this methane, if that comes together with chlorine, you are not anymore able to release the complete electron. You change the atoms. So for example, here, the chlorine will replace one of the hydrogen, then the second, and then the third. This is how you create chloroform. This is not a complete oxidation. This is a substitution reaction, and here you can form disinfection byproducts, especially here chloroform, something that we do not want. Again, this depends on how strong is this molecule, how strong are these bonds, and how strong is this oxidant. The stronger this oxidant that you have, and this is what Philip showed us here before, now especially these ones here, they usually make complete oxidation. They oxidize all the bonds, where chlorine and others are less strong. I think we do not go deeper in here.
Okay.
We come to that.
So next, let's talk about the dried and aqueous solution when it comes to oxidation, right? So you have heard, you know DAISY. DAISY consists of 3 steps. 1, filtration with AFM. Step number 2, coagulation and flocculation using APF. Step number 3, the use of ACO to protect chlorine from photoreduction by the sun and to amplify the natural disinfection power of the sun. And now we're adding a step number 4, which is the use of the DHN, which takes our DAISY system to what we call the DAISY Plus. And this provides swim in drinking water quality.
Yes. So, I mean, whatever oxidants you're using, you know, it's not just a DHN. This is just one of the solutions where we believe at the moment that, according to our knowledge, it's the best.
Sure.
We believe it's the best. Has some disadvantages, but we really believe it's the best. Of course, you can do it with sodium hypochlorite or whatever, but we believe this is a really good solution. And we bring it on the slogan, as you mentioned, swimming in drinking water. Now, and here you see 0.1 milligram per liter of chlorine in the water. Why that low? I mean, you can't do this in public pools, but if you have a well-designed DAISY system, if you do everything according to what we are saying, you can work this Daisy Plus. That means Daisy plus the DHN, this is where Daisy Plus comes, with as low as 0.1 free chlorine for depot disinfection. Why 0.1? I mean, you can go higher, because 0.1 is the maximum value of free chlorine that you are allowed to have in drinking water. This is in Switzerland, in Germany, in Austria. Other countries are different. And this is what we see here. Jimmy from PPG UK, remember this? This I have stolen from you. You know, he made a really good presentation swimming in drinking water with 0.13 milligrams per liter of 0.1 milligram per liter of free chlorine. And I really liked, you know, what he did here, because in the morning after showering, he took a sample of the tap water in his hotel, or maybe it was at home, I don't know. And you see, you know, in the UK, the free chlorine content of tap water is higher. It's 0.45. And if you do the same analysis, by the way, in Edinburgh, you find 0.9. Also combined chlorine, you know, to have tap water to have up to 1 milligram per liter of combined chlorine. That's always a little bit problem for us because the tap water is much less good than what we have in our pool water. Okay, actually, so we want to have it much better than at least this drinking water in the UK. And yeah, we talked a lot first about pool hydraulics. We talked a lot about daisy flocculation filtration, and today we're talking about disinfection and oxidation. And one of the solutions is this DHN. And the DHN, we always recommend to sell it as a complete set. You know, where you have everything on a panel installed, easy to operate, and a complete solution. What does the DHN do? The DHN is able to produce these free radicals. The free radicals that Philip explained us. You see them here, you know, the blue bubbles, and these are the hydroxyl radicals, and the red bubbles, these are the atomic oxygen. As Philip explained us, these are the most powerful oxidants. So it's able to generate these free radicals. Shall I go on, or you want to take over?
Yeah, I mean, yes.
Yeah.
So hydrolysis actually means the splitting of water molecules, rather than what we will talk in the next slide about salt electrolysis, which is similar but very much different. So as a result of hydrolysis, we produce free radicals for the main disinfection. And because we need a relatively small amount of conductivity, of TDS, we also produce a small amount of chlorine for the residual, for the depot disinfection. Someone is drilling a hole above us here.
Thanks.
We have some,
Okay. We tried to stop that.
I thought it was in my head, but I don't think it is.
It's not that heavy.
Yeah.
Drink a little bit of water, that helps.
No, I'm fine.
That's the neutralization process, by the way.
I'm hydrolyzing. Okay.
Yeah. You know, because these free radicals, they are very short-lived. You know, they are generated in the DHN and they oxidize, but you know, after 5 seconds, they are gone. And the water enters the pool, and there we need some depot disinfection, because this water will take, I don't know, 4 hours, 6 hours, 10 hours until it comes back to filtration and goes to the DHN. And this is why we need a small amount of chlorine for depot disinfection. And the lowest you can go is 0.1 free chlorine.
Okay. So you explained this, I think you explained this better than I, but really what are the difference between a DHN and the salt electrolyzer, right? There's 1 or 2 significant differences. One of them is the cell that we are using, which is a monopolar cell, which means you have a number of cathodes and anodes.
This is, you see here, you always have, this is anode, cathode, and if you change polarity, it's just the opposite. But each of them has a current on it. Florent, could you stop it?
Okay. You may not be able to hear this, but we have some construction around us. It's really annoying. So anyway, sorry for the interruption.
So you have to, this is a difference between monopolar cells and bipolar cells. Here you have minus, plus, minus, plus. In a bipolar system, you have here 1 plus, you have here 1 minus, and in between you have slaves. Now, we buy this from Sugar Valley. And Sugar Valley went to these monopolar cells. They did it because of scaling of calcium carbonate, of limestone. Because obviously, if you have hard water, then you get scaling. And if you have here just slaves, it's much harder to release them. You have minus and here a plus, and between you just have slaves. So you get scaling from limestone. And if you change the polarity, this limestone should go away, but of course not so well on the slaves. This is why they went to these monopolar cells. When they did it, they found out 2 things. The monopolar cells, you can work with a much higher amperage. So 15 amps, it's low voltage, high amperage. And it's really the amps who split.
That's the strength, huh?
That's the strength, yeah. These are the numbers of electrons which are flowing. It's really the amps, who are doing doing the job. That means also, the bipolar cells, you can work just in a short range, between 3 to 5 grams of salt per liter of water. Where with these monopolar cells, this is what you see here, you can work, with no salt, with 0 salt, or up to 10%, 100 grams of salt in 1 liter of water. What else? So to summarize, monopolar cells, they are much stronger. They give much higher. Yes, tell this idiot he should stop. I'm not talking about Philip. I'm talking about the worker up here. Sorry for that. So it's much better. They are much more robust against scaling. They have, they can work with each salinity, and they can not just only split salt, but they also can split water.
Okay.
I leave that to
This
you.
is great. So we were talking about splitting salt, splitting water. So naturally, let me explain this graph here real quick. We have here the production of free radicals that goes up or down. We have over here the production of free chlorine. And in the horizontal, we have the TDS level, right? So if we operate at a very low TDS level, then the DHN will produce a large number of these free radicals, and it will produce a small amount of chlorine. As we increase the TDS level, then this is starting to change, as you can see. You're starting to produce more free chlorine and fewer free radicals. So naturally, I think, also a DHN wants to split salt. But if there's no salt, it has to split the water molecules.
Exactly. It's very easy to understand. DHN is like human beings, or let's say like man. Me, man, always go the easiest way, right? Like the water, we try to get the easiest way. So it's much easier to split salt into sodium and then chlorine than to split water into free radicals. And this is, if there is no salt here, then it will start to split water molecules into free radicals.
Exactly.
Good. We got that.
Yep.
So ideally, we recommend to operate our DHN with a salinity between 1 kilogram to 1.5 kilogram.
Yep. Perfect.
You can go higher. You can also go a little bit lower. So the beauty, of this DHN, it comes all together. It measures the pH and it doses the pH. Can you give me the command? So we have here the pH sensor. We have here the pH pump with a suction lens. We have a free chlorine. You can have it also just with Redox, or we recommend free chlorine. You can add additionally here, this is the red probe, Redox. You also could add conductivity to control the salinity. You have temperature, you have flow. And here in the cell, you produce the chlorine and the free radicals, depending on the salinity that you have. On top, this controller here also can control your pump with timers in 3 different speeds. So low filtration for night, medium filtration for day, and high speed for backwashing. It also can operate your Besco valve if you have that. You also have automatic dosing pump for APF, so you have this, and you can even control pool lights and things like this. And the other beauty is you always have it, it always comes with a Wi-Fi model. So you can control all these parameters and check all these parameters on your mobile, or it comes with a touchscreen, or on your computer. So, you know, for the end user, it's more on the mobile where he can check his values, where he can get an alarm. And for you as a pool builder, it's probably more on your computer where you have all your customers, you know, with the different values. And in the morning, you see who is smiling. Okay, I don't have to worry about these. Who is not smiling, who is crying. Let's have a look what's wrong. And then you see here, can't read it, but it's high or low pH. My eyes are not anymore good enough to read that also.
It's low chlorine.
Low chlorine.
Low chlorine.
Okay,
0.2 in this case.
This is why we work here as a team. He sees better. So yeah, I think it's really something very good. The important thing is we do not want to sell a DHN. We only want to sell it as a Daisy Plus. So Daisy is really the base, and then the DHN is the plus. So always in combination with a Daisy, because only with a Daisy you can reduce the oxidation demand by 80%. Yeah. Only with this you can go to 0.1 free chlorine and not have algae or microorganisms. And as you have seen, you know, we don't, you know, with other suppliers, and I remember once a nice customer meeting that we had in Italy with a rocker, where the speaker before me, you know, he said, yeah, with us, you can have pH as an option, you can have Redox as an option. And then I came and say, well, we are Dryden. We go for the best. We don't give you any options. We do quality without compromise. It comes always with free chlorine, pH, Wi-Fi. But we don't give you an option. We want to go for the best. We are not going for the cheapest. We want to go for the perfect solution. Quality without compromise. Clear statement.
Yes, very clear. And we have also created a great video, a video that is, how long? 20 minutes total, I think?
20 minutes. Huh?
It's installation, it's service, it's operation, everything in there you need to know about your DHN.
Yeah, so you also get a manual, but you know, we see people are not reading any more manual, but if you go through this, you find everything. Actually, if you say we, it's not Philip and me, it was Florent who made really a fantastic job. Yep. And we have this in 6 different languages that you see below here. So yeah, these are the languages, even in Chinese.
Yeah, if you want to learn Chinese, then
welcome. Well, the Chinese version is not ready yet.
Yeah.
By the way, that brings me also to the point here. Here you see, that's part of the video. Here you see salt. This is no normal salt, sodium chloride. And here you see magnesium chloride. And this is what we recommend. You don't have to do it. You can work it only with salt, but we would recommend to use 75% of salt and 25% of magnesium chloride. This, by the way, does not only go with the DHN, this goes with all the salt electrolysis system. And yeah, we explain you why. So. What was this?
Well,
just to show, this is swimming in drinking water.
Daisy plus drinking water, yes.
Daisy plus. This is how Daisy plus looks like. And this is the water that you get. This is the water that you get.
Where is the water?
Yeah, exactly. This was the complaint, you know. This came also from Jimmy in the UK, from one of his customers, you know. His customer called him and said, my water is gone. Where is the water? No, actually he said, wow, you know, I don't see the water anymore. This is better than drinking water. Drinking water will never have this clarity that we can get here. So what is the downside of it? First of all, a lot of people say, well, DHN, this is no chlorine solution. There is no chlorine. This is wrong. It's a low chlorine solution. And it's also not a non-corrosion risk. It's a low corrosion risk. And really the risk is in your hands. And it's really in your hands, and you have the responsibility to make it that you don't have corrosion. And this is why we come now to corrosion risk and to chlorides, etc. Mm-hmm. And the Langelier Saturation Index, LSI. This is how corrosion looks like. Huh? Good. Chlorides. This is what did we have here? Okay, yeah. Mm-hmm. You want to take the first part? I explain then the lower part.
Yes. Okay. So chlorides are one of the drivers of corrosion in a pool. Huh?
Yeah. Or let me start maybe here. What I learned, or
that's okay. Go ahead.
Yeah, no,
Go
I
ahead.
wanted that you explain, the difference between salt and magnesium chloride.
Okay.
But first, I'm 30 years in the pool industry, and 25 years for me, it was clear. Corrosion comes from chlorides. Chlorides is the Cl minus. Are the chlorides, right? And of course, if you add salt, sodium chloride, here you have 1 sodium, 1 chloride. Magnesium chloride, there you have 1 magnesium, 2 times positive charged, and two chlorides. Yep. So I was told, Dominic, depends on the chlorides, and the maximum value that you can have for V4A or 316L, or the journal number is 14571. The maximum value you can have, it depends a little bit on the supplier, it's 600 milligrams of chlorides per liter. And if you have V2A 304, it's 200. And if you want to go lower, higher, then you have to go to a duplex stainless steel, for example, 14539.
Austenitic.
Yeah.
Huh? Austenitic stainless steel.
I even can't spell it. Too stupid for that. In Marbachine, by the way, I think they call it duplex or super duplex. Yeah. However, but we thought all the driver is really just about the chlorides, and this is wrong. This is really wrong. Yeah. Mm-hmm. So let's go a little bit deeper. Philip, you want to explain the TDS?
So TDS means all ions in the water, all dissolved substances in the water. Huh? These are ions that are being measured, and they are expressed as milligrams per liter. Huh? And there are now 3 different terms. There's TDS, there's conductivity, and there is
the chlorides.
The chlorides, and you can compare them to each other. And this is what you have here.
Yeah. To give you an example, if you have tap water, you have maybe, let's say, 200 TDS. This may be calcium ions, this may be a little bit of, I don't know, magnesium ions, maybe a little bit of salt. If you add salt to the water, sodium chloride, 1 kilogram or 1 gram of salt in 1 liter of water, then you add 1,000 milligrams of salt. One gram is 1,000 milligram to 1 liter of water. You add 1,000 ppm or milligrams per liter of salt. This is the TDS will go up by 1,000. So what did I want to say? I come back to so tap water, for example, has a TDS of 200. If I add then in 1 cubic meters of water 1 kilogram of salt, again, this is 1,000 milligrams per liter or 1,000 grams per cubic, then my TDS goes up by 1,000. Mm-hmm. Part of this is sodium, part of this is chloride. Mm-hmm. Now, this TDS is the amount of these ions in the water. Now, it's quite difficult if you want to find out how much of TDS you have in the water. It's kind of difficult job to go to the water and to count the different ions. Okay. That's relatively difficult. Chlorides you can measure, with these droplets. There are some droplets, where you take water and then you add the droplets, and when it changes the water, the color, you find it out. But the easiest way is to measure conductivity. Conductivity depends how much ions you have in the water. So the more ions you have in the water, the more you have conductivity. What means conductivity? Conductivity means how easy it is for electrons, you know, if you have a current, if you have electricity, how easy it is to flow through the water. Mm-hmm. If you have deionized water where there are 0 ions in the water, electrons cannot flow through the water. There is no current, cannot pass the water. Conductivity is 0. If you add then salt, you add ions, you increase this conductivity. And actually, it's really this conductivity that you really can measure easily. You know, these are these hand meters, which cost, I don't know, 20 euros, and that you can put in and you can measure the conductivity.
And this is expressed as microsiemens, huh?
Yeah, microsiemens.
It's an electric current, basically, huh?
Yeah. I guess so, yeah. This is microsiemens. Now, if you divide this conductivity by a factor of roughly 1.6, you get to the TDS. So you always measure conductivity, and if you divide this conductivity in microsiemens by 1.6, you get roughly to the TDS, okay? For example, the conductivity meter that we give, the manual one, already makes this calculation. You know, it measures conductivity divided by 1.6. So it will measure, for example, 2000 microsiemens on conductivity, but on the reader, it will tell you, Dominic, you have 1200 TDS. And the 1200 TDS, okay, it's also just, it's approximately this. If you divide this by 2, you have your chlorides. It's not 100% like this, but approximately conductivity divided by 1.6 gives you the TDS. TDS divided by 2 gives you the chlorides. So here you see these formulas, and here you see the example. So this would be exactly our tap water has already 200 TDS. Then we add 1 kilogram of salt. TDS goes to 1200. If I measure then conductivity, it would be roughly 2000. And from this 1200 TDS, we will have roughly 200 milligrams per liter of chlorides. I continue here, or you take over? Okay, why is this? Let's compare quickly salt and magnesium chloride. You know, we have here this salt, sodium chloride, 1 kilogram that we add per cubic meters of water. So we increase the TDS by 1000 milligrams per liter. Salt is 40% of the weight is sodium, 60% is chloride. So if I add 1 kilogram of salt to the water, again, I increase my TDS by 1000. 600 of these 1000 is chlorides, 400 of this is sodium. Now you also see, you know, where I said 1200 TDS divided by 2 brings you to the 600 chlorides. Now, if you would start with deionized water, you know, you have 0 TDS, you add 1 kilogram of salt, then you have 1000 TDS, you divide it by 2, you get to 500, which would be wrong, but only 20% wrong, which is still good enough. Magnesium chloride. Magnesium chloride is not a powder, it's more flakes. This is flakes, but it's also, yeah, it's in a fast form.
Yeah, in a solid form, yeah.
And it's only 50% concentrated, so 50% is hydrolyzed water. So it's only 50% concentrated. So if I add 1 kilogram of magnesium chloride, then my TDS only goes up by 500 ppm. So half of it is water, the rest is really the magnesium chloride. Here you see it's different because we have on 1 magnesium, you have 2 chlorides. So the magnesium is only 25% and the chloride is 75%. So out of this 500 ppm, 375 ppm will be chloride and 125 ppm will be magnesium. So on the chloride value, you see it's not a big difference. And this is why if we say add 1 kilogram of salt or magnesium, you can take it more or less equal. Let's say you have a pool of 100 cubic meter and you want to add 1 kilogram in average of salt. That would be 100 kilogram. So that would be 3 bags of salt, 1 bag of magnesium chloride. And you would get then more or less to the same value.
But magnesium chloride really also has some advantages over sodium chloride, right? Because it is 2 times positively charged, the magnesium, right? So it acts very good as a coagulant. It's able to coagulate phosphate, for example, which I think also makes the water look more blue in a way.
Yes, it makes the water really clear. It makes the water look blue, and they take the phosphates out. You know, it does the same job like no phos. It's a little bit less efficient than no phos, but you add much more. And that's why you remove really the phosphates. I just see we are a little bit behind.
Okay.
So let's come to the Langelier Index. This was Monsieur Langelier who invented this, and he said, he developed a number, this Langelier Saturation Index or LSI. And he says, if this is neutral, if this is 0, the water is balanced. If you have a positive, you know, if you have 0.4 or 0.8, you know, the higher, then you have the risk of scaling. If you are negative, you know, especially if you're below 0.4, you get in a corrosion risk. And if you are below 0.8, minus 0.8, you get in a high corrosion risk. And he said this index depends on the pH. The lower the pH, the more negative, the lower the pH, the more I get to the negative. The lower the pH, the more corrosive is the water. The lower the water temperature, the more corrosive is the water. The less total hardness I have, the more corrosive the water gets. The less alkalinity I have, the more corrosive the water gets, and the higher the TDS, so the higher the salinity. Okay, let's make some examples. And again, ideally you want to be here in this range. Up to minus 0.4, it's acceptable. If you go lower than this, you get in an aggressive water. But if you want to take this.
Okay, so there are great calculators online that you can find. This is one that we have been using, Lentec. There are apps for this as well. So
just go on Google, Langelier Saturation Index, and you find this Lentec. Yes. This is my favorite one.
So here we have the 5 input fields. Let's say we have a pH of 7.4. We have a TDS of 1200 milligrams per liter. We have total hardness of 200 milligrams per liter, and we have alkalinity of 100, water temperature of 28 degrees Celsius. And
then
this,
you press on calculate. This is important, otherwise we're not.
Exactly.
Then you press here on calculate,
and then it will show you here the results. So it tells you the LSI, which means you are perfectly neutral and balanced. And it also gives you an indication of what your pH should be to be in balance. And because we are in balance here, it's the same. It's 7.4.
Exactly.
So if we take another example here.
Same values. Now we just change the salinity.
Yes.
The salt concentration. So we add 2 kilograms of salt instead of just 1.
Exactly.
All the rest stays the same.
Yes. So we increase here from 1200 that we have to 2200, conductivity. Everything else stays the same. And now we have a negative LSI, which means the water is becoming what? Corrosive?
Corrosive, yeah.
Corrosive.
But
slightly.
Point 11, minus 0.11. That's this is still good.
And in order to balance our LSI now again, we should increase the pH by 0.1 to 7.5.
This is still in balance.
Yeah.
So you see salinity, 1 kilogram or 2 kilogram of salt doesn't play such a big role.
Yep.
Let's look at the next one.
So the next one, we change alkalinity. We drop the alkalinity from, how much was it? 200?
100.
100 to now 40. and you can see the LSI drops dramatically.
Again, only 1 kilogram of salt, but
Yeah.
The alkalinity goes down, and then you get here, you already get in the corrosion risk.
Water becomes corrosive. Yes. So you would need to increase your pH from 7.4 to 7.8 to balance the LSI again.
I wouldn't do that. I would not go higher than 7.6.
Yeah.
At least not in the pool season. Maybe in wintertime if you just stop it. Okay.
So alkalinity plays a very important role when it comes to corrosion.
And this is something that changed, that we will see, and that you can adjust. Water temperature.
And now water temperature also plays a role. So again, all the same, we have the same parameters, but now we drop the temperature to 10 degrees. So winter
before
conditions.
28, now 10. Yeah.
Yes. And again, the LSI, the water becomes a lot more corrosive.
Exactly. Here, I really would just stop the pH pump, you know, and let go the water to 7.8, and so it's in balance. Then you will have no corrosion.
Okay.
Okay, and the last one, the last one would be the total hardness that you usually cannot. We don't have it here. The hardness, the total hardness also plays a role. Usually, the total hardness you cannot change. Well, you can, because if you add magnesium chloride, what we discussed before, you increase the total hardness, because the total hardness is the calcium and the magnesium ions in the water. So through this we go very, very quickly. You know, you have this lime carbonic acid balance. That means, you know, the water that has some lime and the carbonic acid. This is in balance, and you have a certain alkalinity. So if you fill the water, you know, this is balanced. Now you increase the temperature. You use the pool. By increase of the temperature, you know, the calcium carbonate falls out, the CO2 leaves the water, and this is where your alkalinity drops. You know, alkalinity, Philip showed it before, it's HCO3, and you see here we lose CO2, so this is why if we lose carbon dioxide to the atmosphere, you know, our alkalinity drops. So if we increase the temperature, and if we move the water, we release carbon dioxide to the atmosphere. pH goes up, alkalinity drops. If you add then acid, then you bring the pH again down, but you also decrease alkalinity. So with each liter of pH minus that you dose, you decrease your alkalinity. And the only way how you bring your alkalinity back is if you have fresh water, and this fresh water is hard, has a certain alkalinity. If it's really soft, like in Scotland, it will also not help you. The other way is really you have to add Alka Plus. I make a little bit promotion for Bayrol. If they are on the call, Alka Plus from Bayrol, which is sodium bicarbonate. There are other manufacturers as well, of course, but it's really the Alka Plus, you know, where you bring back alkalinity. Again, alkalinity is this here, HCO3. This is alkalinity. Yeah, if you dose pH plus liquid, you know, which is caustic soda, you do not change alkalinity. You do really not change alkalinity, really just with the Alka Plus, or also the pH plus powder, I think, has a little bit of bicarbonate in it. We are running out of time. Okay, we finish here the story with one case study, public pool. Again, this is Breitenbach, where I learned to swim. So that's not a new pool. It's quite an old one. And we did here some changes. It was very old installation, and we changed it to a Daisy Plus installation. This is the schemata, so very simple, two filters, DHNs on a complete Daisy Plus system. We talked already about this. We also did some good energy savings, because, you know, they didn't have frequency controller. They had huge pumps, but no frequency controller. So we had frequency controller, flow meters, and this where we made really good savings in energy, but we don't want to talk about this. I want to talk about the water quality, you know, and you see two things, you know. So we are really well with the combined chlorine, 0.15. The limit is 0.2 in Switzerland. THMs, it's 0.015 milligrams, or in micrograms, 15. The limit would be 20, so this is also really good. Chlorates that we talked about, you know, where the limit in Switzerland is 10, in Germany it's 30, in many other countries it's not measured, less than 1. So, you know, because of these free radicals, or to be honest, I even do not know why it is, but we have seen with this DHN, you get excellent chlorates value. Turbidity, yeah, not anymore measurable, really, really good, beautiful. Really good. And no corrosion, as you can see here, these are stainless steel. If you check really the alkalinity, this is important.
Good.
Yeah.
That's it. We're
yeah,
at the
today
end.
It's a little bit more my subject, the DHN, than yours, because
okay.
in America we are not selling this. This is why I took a little bit a bigger part. It's not because he is still suffering more than I am from the whiskey from yesterday, but session number 8, and this is my favorite session. So please join us on this. We will talk about public pools. We will talk about the 5 different ways. We come back also quickly to activate the carbon anthracite, but then really we will talk about treatment, disadvantages, advantages and disadvantages of UV medium pressure for dechloramination, the system wave ozone, and here this is brand new, this is world new, advanced oxidation, Advanox, so that will be a good one, I'm sure.
Definitely.
So same time.